Okay, we're going to continue with section 3.1. And I'd like to start by responding to a question. It was been asked whether or not you can have a function whose maximum and minimum on an interval were exactly the same value. And the answer is yes. So let's just take a look at an example. How about we have f of x equals a constant. Let's say f of x equals 3. We know what the curve y equals 3 looks like. It's just the horizontal line at height 3. Let's say our interval is, let's say 1 to 4. So this is an interval of x values. 1, 2, 3, 4. I took the closed interval. So what we're concerned with is all parts of the curve between x equals 1 and x equals 4. So this little piece right here. And you can see that any x value here is at least as high as any other x value. And if you recall the definition of an absolute max in an interval, you don't have to be higher than any other point. You have to be at least as high as any point. So every point in this interval is an absolute max on the interval. Likewise, every point on that interval is at least as low as every other point. And so you can see that every point in here is also an absolute min. So the absolute max is at height 3, and that occurs everywhere between 1 and 4. That's the interval that we were given in the problem. And every point between 1 and 4 is also an absolute min, and that also occurs at height 3. So the absolute max and the absolute min can occur all at one height. And this absolutely, no pun intended, has a maximum. The maximum height is 3. It absolutely has a minimum value. Its minimum value is 3. That it doesn't go higher than 3 and it doesn't go lower than 3, but it does attain 3. So at the end of last class, I asked you a question, which was, under what conditions on an interval I and function f can we guarantee that f has an absolute max and an absolute min on I? And after the examples last time, I think you have some idea. There has to be some things true about I, and there has to be some things true about f. If you're not clear on the examples that we did at the end of last class, an advantage of the videos is you can just go back and look at that video again, at least the end of it. But the answer to this question is encapsulated in the following theorem, which is the second big theorem that we will see in Calculus 1. So the extreme value theorem. We're going to abbreviate this EVT. EVT for extreme value theorem. As usual, we have some hypotheses. If some hypotheses are true, then our conclusion is true. So if the first hypothesis has to do with the interval. If I is a closed interval of the form AB. So we include both endpoints. It's a closed interval. And so that's the thing that has to be true about the interval. The thing that has to be true about the function, and you may have guessed this after our examples at the end of last class, f is continuous on I. You remember that last example I gave you last time. We had a closed interval, but we had a discontinuous function. And that didn't have an absolute max or an absolute min on I. So if I happens to be a closed interval, so we don't allow from negative infinity to infinity, and we don't allow the open interval from 1 to 3, if it's a closed interval and f is continuous on I, then f has an absolute maximum and an absolute minimum on I. The extreme value theorem. You can also find this in your textbook in section 3.1. The wording will be slightly different. So if the function isn't on a closed interval, maybe it has a maximum, maybe it has a minimum, but who knows? It depends on the situation. If the function isn't continuous on the interval, maybe it has a maximum, maybe it has a minimum, maybe not. It depends on the situation. But if both these things are true, you can guarantee that the function has both an absolute maximum and an absolute minimum on the interval I. So I want to give you another definition now. We say that a function f has a relative, and a synonym for relative is local maximum at x equals c if there is some open interval containing c upon which f has an absolute maximum at x equals c. So have a look at that for a second. I think the first time you see a definition like that, it might be a little confusing. Let me put it a little bit more colloquially. So in other words, x equals c is the highest value in its vicinity. So it's the highest value in its vicinity. So similarly, we can define a local or relative minimum. F has a relative or local, those are synonyms for each other, minimum at x equals c if at x equals c we're at the lowest value in the vicinity. And again, if you have any question about this, this would be an excellent question to ask during office hours. So let me take a look at a picture. Let's draw a little curve here. Your picture doesn't have to look exactly the same as you take your notes, but you can see that, let's call this x equals a. At x equals a, we're at the highest point in our vicinity. So we have a relative maximum right here. When we get down to this point, we're at the lowest point in our little vicinity here. We're not at the lowest point anywhere, but we're at the lowest point in our vicinity. We have a little region around here where we're at the lowest point. So at x equals b, we have a relative min. Here we have another relative max. Again, we're not at the highest value anywhere on this curve. You can see we're higher here. In fact, we're higher all the way over this hill, but we're at the highest place in its little vicinity. So we have another relative max here. Let's call that C. Another relative min at D. Another relative max at E. So it's possible to have more than one relative max. And it's possible to have more than one relative min. Just like in a mountain range, you can have more than one mountaintop, and they can all be at different heights. The mountaintop is nothing more than the highest place in its vicinity. So we're looking for mountaintops and the bottoms of valleys. Now what I want to ask is, what does the function have to look like at a relative max and a relative min? So look at our 1, 2, 3 relative maxima, our 1, 2 relative minima on our picture. At this first one, at the top of this hill, I think you can see that the derivative is 0 there. And the derivative is 0 at the bottom of this valley. The slope of the tangent line is 0. Same with the bottom of this valley. Same with the top of this hill. At that point, things are a little bit different. We actually don't have a derivative there. Remember, having a derivative means that the curve is smooth there, and the curve is certainly not smooth at that peak. So you could never have a maximum where the derivative was positive, because if the derivative is positive, you can always go uphill by scooching a little bit to the right. Likewise, if the derivative is negative, you can never be at a maximum because you can always move uphill by scooching a little to the left. If the derivative is positive or negative, you also can't be at the bottom of a valley. If you're going to be at the top of the hill or the bottom of a valley, the derivative either has to be 0, like it is at these points, or not exist at all. So I'm ready to give you the next definition. Function defined at x equals a, let me say x equals c, has a critical point at x equals c if either f prime of c equals 0, if the derivative there is 0, like it is here and here and here and here, or f prime of c does not exist. Which either means the curve is broken there, or maybe it has a vertical asymptote, or as in this picture, it has a sharp turn. So the definition of a critical point is an x value where the derivative is either equal to 0 or doesn't exist. And I think you won't be surprised by the next proposition. If f has a relative maximum or relative minimum at x equals c, then x equals c must be a critical point. Either the derivative is equal to 0 or it doesn't exist. So if we are at the top of a hill, if we're at a maximum or the bottom of a valley, either the derivative equals 0, and I've cleverly erased that picture, but I'm sure you still have it in your notes, or the derivative doesn't exist. Either the derivative equals 0 or the derivative doesn't exist. In other words, x equals c is a critical point, which means one of these two things is true. I have one more question for you. Are all critical points relative maxima or relative minima? Are all places where the derivative equals 0 or doesn't exist tops of hills or bottoms of valleys? Are they the highest place in their vicinity or the lowest place in the vicinity? If you are willing to do it, I'd ask you to pause right now and think it over for a second, because I think you can answer that question yourself. So I want to remind you of a function that we know well, x cubed. And you know what x cubed looks like. It looks like kind of like a parabola, sort of parabola-like on the right, and sort of like an upside-down parabola on the left. And we sketched this function fairly carefully when we were reviewing pre-calculus, and we've seen a variety of different times that the derivative is 0 at x equals 0. The curve is horizontal there for an instant. And yet you can see, if we stand at x equals 0, we are not at the top of anything in our vicinity. We can get a little bit higher by scooching to the right. And we're not at the bottom of anything. We can get lower by scooching to the left. So the answer to this question is a resounding no. And here's an example.